Hi, I'm William reporting for the Fun Robotics Network. I'm here at the Australian Nationals with Team 14380, the Blue BotBuilders. They were the Winning Alliance captain and Inspire Award winner. They were undefeated throughout the qualification and playoff matches. Learn about their active intake that's do both samples and specimens. Learn about their transfer and hashtag slamdown delivery, all on Behind the Bot. When approaching the start of the season, what was your main strategies?
Yeah, from the beginning of the season, first thing we want to do is to be able to accommodate both sample and specimen in the same subsystem. That way we can work better with our alliance partner. And second is to have a fastest cycle time possible to max out our points.
So would you be able to showcase it in taking both samples and specimens?
Yep, so we're going to do a sample first. And now outtake. And now a specimen. So the transfer claw holds on to both samples and specimens once they have been intaked.
So I see that you have compliance on your intake. What was the purpose of that?
Yeah, so the purpose of the compliance arm is to able to intake the samples and specimen in basically any orientation. So we know that in the submersible that the samples can be aligned in any direction. So we want to fix that.
Was there any accommodations that you had to make for the samples and specimens because you were using the same system?
Yes, so we had to intake the samples or specimens like horizontally. That was the only way we'd be able to do the specimens and the samples. And also right here, we see these, we call these the flabsters. We had to put these on our intake instead of a solid roof, otherwise we wouldn't be able to pick up a specimen, we would get stuck. So these are kind of compliant, so the specimen, if you give me a specimen please, thank you. When it comes in here, it kind of gets trapped in here, so we can move over to the high rung. And then when we're ready, obviously this grabs it and then we'd pull it over. And it's able to come up through the top there because of those compliant flabsters.
You use an active intake with a motor. How did you figure out the packaging of that motor with your intake?
So the way we figured out the packaging of our motor with our intake is, so last year we've suffered a lot of power draw issues. So this year we wanted to focus on that. So we've made the motor mounted on our center of mass, which is our pivot. And as you can see under there. So it's right in line with our pivot, which puts the least strain on our cams, which is also another method. And we've also, to save weight and also power draw again, we've used internal 3D printed gears that counter rotate the force. So this is both of these 4 compliant wheels here. They're all driven off of the same motor and with hidden internal gears.
I see that the intake pivots down. Can you explain how that works?
Yes, so instead of actually pivoting the actual intake itself, we pivot these 2 cams underneath here. And so what this allows us to do is use minimal power when pivoting. So when we pivot down, we're going to pivot down like this. It's powered by gravity, and at the bottom, no power is actually needed to keep it at that position. And same for when we pivot up, the intake can just actually rest on these cams here, so no power is needed to keep them up as well.
I also see that you have this server at the very back. What purpose does that serve?
That is the poop chute. So after we've intaked a sample or specimen, we use this to determine, or not determine, but physically keep it in the intake or reject it and fire it out the back. So if the internal color sensor here, if that detects it to be a desired sample, it'll keep this servo up and keep running the intake just to push it against that. And we're holding it until we're outtaking with the grippler. Whereas if we did not want it, it was an opposite aligned sample, we can simply put this down and keep running the intake and it's fired out the back. That's why it's called the poop chute.
So moving on from your intake and your compliance, so it was really pretty cool. Would you be able to showcase, your claw looks really strange. Would you be able to explain your design process behind that?
Yep, so we call the claw the grippler. And we've made it as lightweight as possible. And its primary function just take samples and specimens, transfer it, and outtake it to either the high basket or high chamber. It's designed in such a way that it's as light as possible, using carbon fiber, BBR small servo, and as much 3D printing as we can, while still, mounted on hollow carbon fiber tubes and pivoted by two BBR, Axon Maxes, so we can pivot it out and do a #slam down and for a super quick specimen delivery into the high chamber. Another interesting component of the grippler is that, could you put it out please? The pivot points of these two arms are placed in line with where these rubber bits contact the inside of the sample or specimen, so that if you tug on it, it doesn't apply any torque, and so we're only using power once it's pulling up and down or just changing position. There you go. Yippee.
So yeah, how do you ensure that there's a clean transfer between the intake into your transfer system?
Yeah, so that's actually what this servo horn at the back here is for. And so we actually run our intake a slower version of our intake, so it's bumped up right against our transfer floor, so the transfer is perfect every single time. And also our color sensor, we can use it to detect when there is a sample inside. And finally, we also have a magnet sensor right here that can detect when the slides are fully in. And so once they are fully in, we know we can properly close the claw, so we always have a successful transfer.
So yeah, thank you for explaining about your intake and transfer system. So I see that you've had a very fast and effective 3-second climb. Would you be able to explain that?
So yeah, the thought process behind our climb is we went for a level 3 climb, but we've discovered that the engineering behind it and using our cost benefit analysis, it wasn't going to be worth sacrificing a lot of driver practice time. So we ended up settling for a level 2 ascent, and it's very fast, and if we can get those extra cycles at the end, that's why we've made it so fast. It gets us an extra cycle plus a hang.
So yeah, how do you move your hooked arms to it, and how does that hang actually work from it?
Yes, so we use servos linked by a chain here to actually pivot up the arms, and then once that has been pivoted, then we also raise these to get the slides out of the way for the hang, and then using a motor we drive these hooks down the chain, so then we can climb the low rung, and then we bring back the slides to make sure our center of mass is in the correct place.
So talking about the different odometry that you've used, what type of odometry do you use? Do you use I see that you've used an OTOS and you have some of the BotBuilder odometry wheels. Would you be able to explain your thought process behind that?
Yeah, so at the start of the season, we actually really wanted to try our OTOS, so that's what we went for. But we've had to swap it out because we found that it really depends on what field you're on. And it also depends on like so many other little factors, like if there's aluminium dust on the floor or anything like that, can really throw it off. So we decided after our original competition to switch back to dead wheels here, and they've worked quite well for us. And actually, just before I forget, just want to mention the BotBuilder pinpoint that we've also tried and used throughout our season.
And thank you so much for explaining this awesome robot. Congratulations again on the win at the Nationals. Just such an awesome, beautiful blue robot. Just congratulations again. And thank you so much for sharing. This has been Team 14380, the Blue BotBuilders.